Welcome to a special 15-year anniversary episode of Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today it's my pleasure to welcome Brent Segal. Brent is a technology scout for Lockheed Martin, and he engages closely with small and medium-sized enterprises as well as venture capital firms in this role. Prior to joining Lockheed Martin, Brent co-founded and served as the Chief Operating Officer of NNCO, where they generated more than 200 patents and applications. Brent, thank you so much for taking the time to chat with us today. Can you tell us a little bit about yourself and how you first got involved in nanotechnology?
I was in graduate school working in inorganic chemistry and had made good friends with Charlie Lieber's lab, who is really one of the progenitors of the nanowire carbon nanotube industry, you might say. And my good friend Tom Rukas there had been telling me about this material, carbon nanotubes, for some time. And he had decided he wanted to start a company to actually commercialize something in carbon nanotubes. And so he called me and said, Brent, I want to start a company involving carbon nanotubes and I'd like you to help me. And it involves nanotechnology. I had no idea what was going on in this field, but he explained it to me. He said he had worked on a paper for Science. This is in 1999. And the main point of the paper was really that he had taken a carbon nanotube and laid it out over another carbon nanotube and applied a voltage, and the carbon nanotubes came together. And when they did, current flowed, which he called an on switch. And when he reversed the polarity, they popped back out of contact and it was an off. Now, this he called a memory switch and said it could be scaled up to make a very large memory. If you put it in context, imagine if you took a pipe and you laid it across a canyon, and the pipe was, say, 2 feet in diameter and 1 mile long, and you wanted to bend it down and have it touch the bottom of the canyon, it would break very quickly. But carbon nanotubes do not break. And this was an absolutely astounding discovery. And I said, yes, let's do it. So we started a company called NNCO to make nonvolatile memory out of carbon nanotubes. And that's how I got into the game.
You mentioned nonvolatile. Could you explain a little bit what you mean by that?
Well, this is actually the key point is not only can you make these switches, which have, if you will, an on and an off, which gets translated to a 0 and a 1, but even more important is when you remove the power from these switches, they stay exactly in the state in which you found them. And that's what we call non-volatile. Now, this turns out to be a form of memory which back in those days was not so widely used, but is now used in everything. You think of flash drives, the small little thumb drives that everybody carries around with them. That's made out of a type of non-volatile memory. And just about every hard drive has been replaced in most modern laptops with a kind of flash memory, a non-volatile type of memory. So to get into a non-volatile memory space was a really exciting thing.
So that was your introduction into nanotechnology and really as an entrepreneur. What advice do you have for students or others who are thinking about starting a tech company?
Well, let me tell you about what happened when we tried to commercialize nanotubes, and I think this will be the lesson that people will take away. So we had a situation where Tom's wonderful paper that he did at Harvard, it was fantastic. But when we tried to integrate these carbon nanotubes and tried to lay them out in a chip scale or a wafer scale, we immediately ran into some real realities about integration. And it turned out that not all the nanotubes were the same length. It turned out that they had contamination. And it turned out it was really hard to integrate. And we could have just quit right then, right out of the gate. We could have been stuck. But what we really had to do was think in a different way. And so what we ended up coming up with was we took the nanotubes in a completely random array, laid them out on a surface, and then used a very common technique called photolithography to etch out patterns in the carbon nanotubes and leave some parts covered with a chemical species and some parts exposed. And in the parts that were exposed, we found that plasma, oxygen plasma in particular, could remove those carbon nanotubes. And then when we removed the chemical, we now had beautiful, what we called traces of carbon nanotubes at almost any feature size, width, and length that we wanted. And we let the carbon nanotubes interact with each other in this mesh to really solve the problem. And so as an entrepreneur, you will be faced with these problems. You will not know what to do. You will have difficulties, and you have to come up with new ways of doing it, which leads us into patenting. And we had a lot of patents. And one of the things that made us do a lot of patents was understanding these problems that we had run into. And there just was not a solution. We looked here, we looked there, we tried all kinds of different ideas. But when you had a solution that was really new and would solve the problem, we wrote a patent. And that's how you might notice we got quite a few patents.
That was work you collaborated with BAE, is that correct? I remember seeing images that I used in talks about that time frame.
That's right. We did work with BAE, and that would probably bring me to my second piece of advice for entrepreneurs, which is partnership. So here we are, a small company, and we are trying to work on these things. And we realized very quickly we couldn't do it all our own. We did not have some of the big devices. We didn't have the lithography equipment. We didn't have the ability to purify carbon nanotubes. And we ended up partnering with BAE, who had a beautiful fab in Manassas, Virginia. We worked with them. We partnered with ASML, which is the largest lithography company in the world. And they really helped us to perfect how can one fabricate these devices in a CMOS fab. And then we actually partnered with a company called Brewer Science in Missouri, who was very good at mixing different component species together in a way that they could go into a fabrication facility and be very clean. And they helped us to develop a CMOS grade carbon nanotube solution in those days. We also worked with Carbon Nanotechnologies, Inc., CNI, if you remember, Rick Smalley's company at Rice. They fabricated a lot of the carbon nanotubes for us that were quite reproducible. And together, we actually had a group that could actually go to a CMOS fab like BAE and produce parts. It was fantastic.
Yeah, it was very exciting. I didn't recall that you had worked with Brewer at that time. So that's a great story. Can you talk a little bit about the exit? Because you're now at Lockheed Martin, is that correct?
That's right. So what had happened was we had two divisions, and we had a division that was focused entirely on commercial memory. And then we had a second division that was working on things for the government. And these were very coincident because we really needed both things for both constituencies, if you will. But at some point, we quickly realized that the needs in the government division were diverging and that they had very specific requirements that really didn't mesh with the commercial business. And at that time, we decided this is a good time to split the business, and the commercial business went on its own, and the government business was sold to Lockheed. And then I went with the deal, if you will, to help integrate it.
And since you've been there, you've taken on a number of other responsibilities and definitely have a broader view of the aerospace and defense industries. Can you share a little bit of information, other areas where you are seeing nanotechnology play a role?
Yes, I see it really distributing itself in a lot of areas. And I'm sure all of your speakers that you have would agree in some of these things. But clearly, some of the areas that I really think are going to be valuable are batteries, especially trying to improve the power density and the energy density of batteries. Of course, we have nonvolatile memory, and that will go to a lot of other types of electronics. And we could talk more about where that might go. Biosensors, I see a lot of opportunity in biosensors with carbon nanotubes. They are a wonderful matrix for attaching other kinds of molecules. And they're really starting to garner some interest in the sensor field. Solar cells, there are a number of people who are working on solar cells with carbon nanotubes, coatings of all sorts, and even something like paint. I've started to see some additives really making their way towards the market. So I think there's a lot of opportunities there. It's taken a lot longer than I think we all thought, but these things are hard things.
Yes, and as my colleague likes to say, hard stuff takes time. We are seeing mass market applications now after decades of research. I want to switch gears a little bit. One of the things that you mentioned was collaboration. I'd like you to comment on collaborations across disciplines. And I think that this is an area that at the onset of the NNI, it was a novelty to really work outside of your discipline. And that's one of the areas that people focus on when they talk about how the ecosystem has changed. Can you comment on interdisciplinarity and the impact it's had on your work?
Yes, I can. I think that nanotechnology itself, if there's one thing that it did that is absolutely unique, it is to create this opportunity for intersection of disciplines. And never before, I think, had we seen mathematics meet biology and biology meet physics, physics meeting surface science, and of course, being a chemist, I have to say everybody meeting the chemist.
Yes.
In fact, when I was an undergraduate, I tell you, I was very interested in molecular biology. And I went to the head of the chemistry department and I told him, look, I really want to work on molecular biology. And he said, hey, go ahead. But I don't know if you're going to get a chemistry degree at this university because I don't know that molecular biology really overlaps with chemistry that much. And now that's completely laughable. I mean, that wouldn't make any sense. But nanotechnology has played a big role in moving us all together so that we're all scientists and engineers. We're not just physicists or just biologists or just mathematicians.
Switching gears a little bit, could you tell us a little bit more about your interactions with the Center for High Rate Manufacturing, which was funded by NSF?
Well, that started in 2004. And by the way, this podcast, when I thought about it, it really conjured up a lot of things I hadn't thought of in a while. So I thank you for inviting me. That started in 2004, and it was a collaboration between Northeastern, UMass Lowell, and University of New Hampshire. It was really special. We had a group of different scientists and engineers coming together across 3 different universities. And the thing I loved about it was focused on high rate manufacturing. This to me was the real win. That instead of talking about very specific devices in the literature that you could do one time, their entire rubric was how can we leverage our expertise, especially in plastics engineering, to really make things go fast? How can you make millions of devices, not 5 devices? And in addition, they really focused on the environmental product lifecycle impact, which nowadays I would sum up as sustainability. How can you design something and then understand its product lifecycle impact all the way through end of life? And so I really enjoyed that and actually have pursued sustainability all the way through to this day, and I still work on sustainability activities.
Well, that's another example of where collaboration, in this case across universities, had an impact on advancing the technology.
That's right. Some of the things that they did there, I think, were very new in nanocomposites, molding of nanostructures. They had an entire group that started in flexible hybrid electronics, which was really the concept of how do you take electronics and put it on a piece of plastic that's completely flexible? And then how do you make 1,000,000 of those? And I think that area is going to be really, really interesting in the next 5 or 10 years. We're going to see a lot of people doing that.
Looking into the future, What are some of the most significant challenges that will be solved or applications that you see that nanotechnology will play a role in?
Well, I think nanotechnology is going to solve a lot of potential big problems. But we first have a problem with nanotechnology that I think a different field can solve. Artificial intelligence is something I think we can use in nanotechnology and science writ large to increase the speed of learning in our experiments. And I think we can do that by inserting AI as a helper to humans. So let me give you an example from my graduate career, which is fun. We would build lots of different molecules, but the only way we were absolutely sure if we had made a certain molecule was using X-ray crystallography. And in order to do X-ray crystallography, you had to make a crystal. Well, to get a crystal to grow is not an easy thing. And I had the habit of setting up crystal growth chambers and then checking them every day. And if you move the crystals just a little bit, crystals don't grow. I would have really enjoyed using artificial intelligence and real-time computer vision to monitor my crystal growth and have it tell me, you have a crystal, come and look, rather than me influencing it. And that is a similar kind of function that we see in nanocomposites, nanoparticles, generation of nanotubes, where there is a lot of activity in a chamber, growth chamber, or something with a furnace, and we don't know when it's done. And we don't know real time what the status is, which we might call edge computing as a way of monitoring that. So I think that we are on the precipice of helping the nanotechnologists and scientists writ large plan experiments, characterize their outcomes, and then help them scale the really good results so we can go a lot faster. And I'm very excited about this field. I think we're going to see this over and over again in the field coming up in the next year or 2 years.
You talked about how AI is going to impact discovery and research in nanotechnology, but what is the impact of nanotechnology on the hardware that enables advancements in AI?
Okay, wow, taking me back. Let me lay out one area that I think is still in its infancy but is worth exploring. The computer chips that we use right now, even though they have a thickness, they are essentially two-dimensional objects. They are generated on a surface with a three-dimensional structure, but there's only one real layer, one real active layer. And one of the things that nanotechnology can do is to get devices off of the substrate and stack them. And by stacking them, they become real three-dimensional objects and can even be what I would call monolithic computing. That is, we have lots of layers of things. One layer could be memory embedded within the architecture. One layer could be for compute. One layer could be for sensors. One layer could be just to transmit data off of a chip. And we haven't really been able to do that level of integration until now. And I think the technology is starting to become available to see this idea of three-dimensional monolithic architectures, which will speed up computers by 3 or more orders of magnitude. And the reason they'll speed them up is because the time it takes to transmit information will go from one chip transmitting to another chip in a different location, which is a long distance, to devices transmitting maybe just 1 micron or a half a micron or even a few nanometers within a chip. And that's going to make them a lot faster. I can give you one more really odd potential for nanotechnology. The electronics industry right now is a digital platform. It's all ones and zeros. Something that has been observed with nanotechnology and in some of my own work is the potential to have many states so that one could read out lots of different states that are not just 0 and 1, but are between 0 and 1. And between 0 and 1 could be a number of 10 states, it could be 100 states, it could be 1,000 states, it could be 1 billion states, depending upon how easily you're able to read it out. And I think that's another possibility. I would call it analog computing, and you're probably seeing more and more talk about this. That could also be a game changer.
Brent, I want to thank you again for taking the time to chat with us this afternoon. Do you have any closing thoughts that you would like to share with our listeners?
Well, if I was going to start a company out of graduate school again, I would be very excited right now. I would be looking at some of the world's biggest problems and challenges. I would be looking at nanotechnology and the potential to solve some of those challenges, whether it's in the energy domain, the water domain, new electronics, new batteries, even if you wanted to get into metrology, new microscopes. And I would go for it. I think it's a fantastic time to be an entrepreneur. And you need energy, you need perseverance. Of course, you have to raise money. You have to have a fantastic idea. But if you can get all those things together and surround yourself with the right advisors, it is a fabulous experience. And I would recommend it to anybody to try.
Thank you for joining us today for this special 15-year anniversary edition of Stories from the NNI. If you would like to learn more about nanotechnology, please visit nano.gov or email us at info@nnco.nano.gov. And check back here for more stories.